脑理系 and let's have
张志威，大学。各位同学好，我是王伟华，现在中医院的学生。物理，中文大学。
Next, let's have the three teams to introduce themselves, starting from experiment.
So I'm John and fellow competitor. So we are from Kaohsiung Senior High School. I'm Xu Hanyu, and it's Moe, Liu Yong, Luizhou, and Paijin.
Thanks. Welcome.
We are MD Fresh from Mindao High School, and I'm Ethan, YC, Alan, Michael, and Justin. Thank you.
Hello everyone, we're Team Abbas from Chinese High School. This is Mark, Chia-Ting, Sam, and John, and I'm Jane. Thank you.
Okay. Now let's move on to have the opponent choosing the problem. You have 1 minute.
We would like to challenge rulership.
Which one?
Rulership, problem 14.
Problem 14. Ruler trick. Okay. You have 1 minute to decide whether to accept or not.
We accept.
Okay, problem number 14, accepted. So you have 5 minutes to prepare for your report. Yeah, in the meantime, please write down the name of the representative from your team. begin with your report.
Okay. Honorable judges and fellow competitors, this is reporter from Team Salver. Today I want to report it from problem 14, ruler trick. The problem statement presents that when we place a ruler on the edge of the table and throw a ball on it, the ruler will fall. However, if we cover a piece of paper on it and throw a ball again, the ruler will remain on the table when the ball bounces on it. So our goal is to explain this phenomenon and investigate the relevant parameters. Here is the relevant parameters I have done in my experiments. So our main focus is why the ruler didn't fall and how many force is needed to make the ruler flip. So first, let's look into the mechanism behind this phenomenon. So when the ball hits the ruler, it will make the ruler lean over like this. And then there will be a lower pressure pocket under the paper. Therefore, it will be a downward force to make the ruler stay on the table. So this physics is very similar to a suction cup. And then we can calculate the downward force by using this equation. It is good to know that H represents the area of the paper that comes up. It is not the whole paper area. And then we analyze the torque in this phenomenon. When the ball hits the ruler, it will create angular momentum. So the torque can be expressed with this formula. And then we consider about the torque from the left part and the right part of the ruler. And also consider about the air pressure and the paper mass torque. So finally, we can know that if the counterclockwise torque is greater than the clockwise torque, the ruler will flip. Based on this formula, we can get the equation about balance condition. However, there might be some potential complexities, including resilience force or the bending of the ruler. So we need to consider the support coefficients, alpha, to help me correct this error. Here is how we know the support coefficients. So according to beam deflection formula, we can calculate alpha from this equation. And after we fit in our experiment data, we can get the value of the alpha. So back to our theory. Because our goal is to analyze how many force is needed to make the ruler flip. So in the experiments, I control the S equal to D and equal to half of a ruler. So the critical force can finally express with this formula. And here's how we measure the pressure difference. I place the cell phone on the table like this, and then we use phoenix to know the pressure difference. From the chart, you can see that when the ruler flips, the pressure will experience a quick drop over here. It's equal to 0.38 HPA. And then we consider about the experiment outline. So first, in my experiment, I will introduce suction model vs ruler trick model to analyze the critical force. And in second part of our experiments, I will analyze relevant parameters. So here, I want to explain how the suction model works. So from the video, we can see that the force arm is equal to the resisting arm. So theoretically, the force of the ball will be equal to the force right here. And then, because it is hard for us to measure the force right here, we use the suction model to simulate this phenomenon. So the critical force is basically will equal to the upward tension. Here is the force sensor I use and the graphical analysis software I use in this phenomenon. And then I want to introduce how we use the ruler trick setup to measure the critical force. First, I use a stick board to fix the initial height, and also I control the position of the paper and the ruler. And here's how we get the critical force with the ball. So I increase the drop height every single time, and until the drop height is enough for the ruler to falling down. So in this case, you can see that when the height is equal to 63 centimeters, the ruler will flip. So we can import this video into tracker and to know the change in the velocity and the contact time. Here, I want to clarify what is a flip, because sometimes the ruler will fall down the table, however, the paper still remains on the table like this. But I think this is not a flip. In my definition, flip needs to be like this. Paper fully leave the table. Therefore, I can calculate the critical force. Okay. In our first experiment, I changed the length of the ruler and used 3 different materials, including copy paper, drawing paper, and newspaper. So here's a demo experiment video of our experiment. And then I record the data from the force sensor, and then here's our experimental data. You can see that when the length is increased, the critical force also increases. And also we can know that the drawing paper requires more force than the other 2 materials, and it is reasonable because in our formula, the m of mass of the paper and the area of the paper will also influence the critical force. And then I use the ruler trick setup to measure the critical force with the same paper. Here's the experiment data. You can see that the trend is similar to the suction model. However, it is much lower than the theory, and I will discuss this point later. So, yes, you can see that the real critical force is much lower than our expected. So, I will discuss this point after. In our next experiment, I use 4 different paper and use four different paper with same area and use different width and length to do the experiment. Here's our experiment video. You can see that when the ratio is closer, ratio means the width divided by length. When the ratio is closer to 1, means the shape of the paper is closer to a square, that the critical force will increase. And it is also reasonable because in our theory, if the small l increase, the critical force will increase. And then we use the ruler trick setup to measure the critical force. And then here is our experimental data. You can see that the trend is also similar to the suction force. However, there's a blank right there. There's no data, and this is because the ruler broke. In my experiment, the critical force is much bigger than the ruler can bear. Like this, the ruler will broke. So we can get the real critical value in this situation. And here we compare the suction model with theory and the ruler trick setup. We can see that the suction model is close with our theory. However, the real critical value is lower than our expected. And I think the main reason might be related to the airflow, because when the ruler flips, there might be some airflow into it. So I use the flow 3D to analyze the pressure under the paper. Here's a brief layout of my simulation. From the video, you can see that if we use 3 different speeds of the ruler flipping and use a pressure index to measure the pressure. From the video, you can see that when the ruler flip is much faster, there will be the space under the paper will be closer to vacuum. Therefore, contributing to a greater delta P. And then we analyze the different point under the space of the paper. Here's the data. We can see that in the first stage, the ruler flipping will disturb the gas molecules around it, so result in isolation in the air pressure. And in stage 2, when the ruler touches the paper, the low pressure pocket will form up, so leading to a quick drop in the air pressure. So finally, I think the reason why the real critical value is lower than our expected is because we didn't consider the ruler flip, because the ruler flip is too slow, result in a low pressure difference, so it makes it easy to flip. Now it's our next experiment data. You can, I drop the ball with different masses, and here's the setup of my experiment. From this experiment, we can see that when the drop height increase, the deflection angle over here. Here's the deflection angle, means the ruler flip a little bit. So if the drop height increase, the deflection angle also increase. And then when we drop the ball with heavier, with a bigger mass, the deflection angle also increase. Like this. However, there's also no data in there, and it is also because at this point, the ruler flip. So there's no deflection angle here. So in my conclusion, that's back to the problem statement. We use pressure difference, torque analysis, and critical force to explain this phenomenon, and also investigate the relevant parameters. First, we compare the structure model with the volumetric setup, and we can see that when the length grows up, the force will increase. However, the real critical force is lower than our expected, and then drawing paper will require more force to pull it up compared to the other two materials. Also, we observe that when the ratio is closer to 1, the force will increase, and the real critical force is also lower than our expected. And the joint paper also requires more force than the other two. And we use simulation to know the reason of the low critical value. Is the flipping speed too slow? The pressure difference will be slow, so the critical value will be down. And then finally, we compare the different masses of the ball. We can see that when the ball mass is going up, the deflection angle will going up. And then there's the critical height that makes the ruler will flip. Also, we can find that if the height increases to a critical point, like here, the deflection angle will stabilize. So the critical height right here, if the ball is heavier, the critical height right here will be lower than when we drop the lighter. So here's my report. Okay, thank you.
Okay, thank you. So let's have a question from the opponent.
Okay, so in the short question part, first I would like to ask the reporter about, do you agree that the problem statement is all about discussing the boundary conditions? Yes or no?
I think the problem statement acted to explain this phenomenon and investigate the relevant parameters. So it didn't set out a specific direction of the research.
Okay. Next question. So, do the ruler's insertion depth is the main important factor of this phenomenon? Do you agree?
Can you clarify your screen?
The ruler's insertion depth, like this, the depth, it's not important.
Because, you mean that
Yeah. Do you think that is that important?
I think because our focus,
yes or no?
Because
Okay.
I think that will affect us.
Okay. So, what exact parameter is the main parameter of this phenomenon? You think?
I think the size of the paper and the length also affect.
Okay, thank you. So, you use elastic ruler, right? Is that correct? Okay. So, do you control the initial rotation of the ball?
Yes, I tried doing. Yes.
Okay. So, what about your simulation? Is a two-phase flow or three-phase flow?
Well, initially I want to use 3D layout. However, I think a 2D layout is enough to explain the phenomenon.
Okay. So, is there any oscillations that you observe about the ruler?
You mean the oscillation of the ruler?
Yeah.
Yes, I have.
Okay. Okay. And is the energy loss in the phenomenon is that important to the phenomenon?
Yes, there must be some energy loss in the phenomenon.
Okay. And the next question: do you agree that Young's modules of the ruler may be a factor of this phenomenon?
Yes, I think Young's module not only a ruler but also the paper will also
Okay.
affect the phenomenon.
This part.
Okay. So please prepare for your discussion with the reporter. You have 3 minutes.
Honorable juries and fellow competitors, I'm the opponent from Team Alpha's Xinjiang High School. And today I'm going to be opposing problem number 14, ruler trick. So here's a problem statement where we need to investigate the ruler on the edge of the table, and there is ball thrown at its free end. And so the ball ruler will fall if the ball is thrown. However, if a paper is covered, so that it will make the ruler maintain on the table and not falling from it, and the balls will bounce off the ruler. So there will be two main focuses. That is why the ruler didn't flip off, which is the opponent thinks that it will be related to the boundary conditions of this phenomenon. And also, how did the relevant parameters affect the motion, which the reporter has investigated. And about the reporter's structure, he has an observation video which shows clearly about the slow motion of his phenomenon. In a theoretical model, they have the torque balance equation, and they have the supports coefficient, and also the suction model to verify their pressure. And their setup, they use the thick ball and ruler and also paper to do their experiments. And they also use pressure meter. And in the experimentation, they have the paper's ratio and other material properties, and also the mass of the ball. And for the conclusions, they conduct that the mass is proportional to the height, and also the critical height will cause the flip of the ruler. For the strong points, they have a great fluency of the reports, and their experiments matches the statements which the problem statement asks. And they have a great simulation of their experiments to verify their pressure zones information. And they have well time management. And about the weak points that they can tell more detail for the theory, and there are more variables that can be discussed. And so let's move on to the discussion part, shall we? Okay. So in the beginning, that I would like to ask you, so there is a boundary of your ruler, right?
Yes.
The ruler shooting angle.
Yes. I think the boundary is like the critical height. So if the height increases to a certain point, then the ball will make the ruler flip. Yeah. So I think there's a boundary condition in the critical height.
Okay. So this critical height in your experiments, it's related to the height, right? But in some points that when the ball's mass is too big and the height is too high, that the boundary will be examined, right? That can be observed.
Let me explain. Just we increase the height and just draw the ball, right? So at certain points the roll will flip like this. However, if the paper is too big or some condition, that's the critical height will be too big. That's if the ball falls on the ruler will directly broke. So in my experiment data, you can see that in this condition the critical height is critical force is too big for the ruler, so the ruler broke.
Okay, so since that you have found things like the boundary condition, and I would like to be discussing about the problem that we have clarified in the short discussion. Where can we may I use the blackboard? Sure. So here, I would need to verify again about if this is paper, then this is your ruler. What will be the depth that's just inserted?
Oh. Okay, so I can show you my video.
Sure.
Okay, so in this video, I have just said that the force arm will be equal to the resistance arm right here. So the drag will be half of the ruler.
Okay, so this part, opponent would like to ask the reporter about if it's about the how length of the ruler, then at this part, what will the force that given from the pressure won't be uniform in opponent's opinion? Do you agree?
Yes, I agree that I think it is a good point, but
then what do the reporter think about the uniform force applied?
just in my theory, I consider the pressure difference called a force, and because to simplify the phenomenon, I just think of it just only on the uniform.
Okay, so in this part, the opponent suggests that the reporter can do more detailed investigation about it, or maybe if we are discussing about the pressure difference, that we need to have a uniform pressure, maybe we can that the ruler as the top of the paper that you agree will be more able to have a uniform force applied on it.
Well, I think the force caused by the pressure difference will only affect on the area that the paper pumps up.
Okay, so the depth of the ruler creates the low pressure zone.
So I think can you rephrase
The
the question?
depth of the ruler creates the low pressure zone, right?
Yes, I think
So
the depth of the ruler will affect will affect the low pressure pocket. But in my experiments, I just control the depth of this, so I don't think it will affect my experience.
So let's move on to your experiment about the pressure that you use the suction model, right? You use the force gauge to pull up the paper.
Okay.
Then you pull up the paper from the middle of it, right?
Yeah.
So if you pull up the paper from the middle of it, then so does that mean that the deviation of, and can I see the deviation part where your theoretical part compared to the one with ruler added, like?
Oh, you mean the comparison between these two experiments?
So in opponent's opinion, maybe the deviation is caused by the you live in the middle, but the low pressure zone is actually a small part, so that causes the deviation.
Yes, I think the area that the pressure difference affect on will just that the deviation will affect our experimental results. So therefore, there's some deviation on it. So I think that's one of the reasons. But in my experiment, I have explained that I think there are another reason that is caused by the airflow from.
Oh, so yeah, for the low pressure zone, it's only a small part that the airflow flows in, right? It's the part that when you do the experiments, the pressure, low pressure part will be like uniform like this. But when you are having a ruler on it, the low pressure zone will only be left by the ruler, right? So
Yes.
the airflow will only be at this side, so this might cause the deviation.
Yes, I think it is one of the
Okay.
reasons, but also I think the main reason will about the airflow.
Okay.
Yeah.
The airflow. And so what the recorder means is that when the airflow flows in, that it gives a smaller pressure difference that leads to the forces
Well,
deviation.
Yes, I consider this will be related to the speed of the ruler. So.
Okay, so now we have an agreement. Then let's move on to how do you measure the force that is produced?
So you mean
Like you drop the ball, and how do you get your force data?
Okay. So I said I increase the height of the drop of the ball, and I find the critical height. Therefore, I can export this video into the tracker. However, this
Okay, so you use tracker,
Yeah, I
and
use tracker.
at this part you only measure the initial part of the bouncing, in the initial part of the balls that bounce.
Oh, because
Is that correct? Yeah, the initial part for calculation for the velocity in order to get.
well, yes, we can get the
Okay.
velocity difference in this.
In this part, the opponents agree with the reporter that they have done a great examination for the force that is produced. And for our next question, it will be that if you have mentioned that you use a elastic ruler.
Yeah.
So, and if it's a elastic ruler, there will be a deformation that is proportional to its Young's modulus.
Yeah.
And when there is deformation, which means there will be oscillations of the ruler.
Well, I think there might be some oscillation. Also, you can see the video. One of the video.
Yeah.
Yes, the ruler it bounced out.
So
and I noticed, and I think it is a good point to discuss.
Yes,
But I think it won't affect much about the critical.
But as the second video shows, if the contact time is more about it, as more the ball contact more on it, then the damping of this oscillation will be a factor of this phenomenon, right? In the opponent's opinion.
You mean the damping of the
Yeah,
ruler?
because the ball stays on the ruler for a short period of time. Then the damping of the ruler's oscillation will be a factor.
I think because we calculate the critical force by using the change in velocity, and we didn't. So I don't think that.
So you agree there will be deviations that we can discuss in the future.
I think it is a good point to discuss, but I don't think it would affect much about the critical force I mentioned.
Okay, so what about, let's think of a scenario where your ball is given a rotational momentum that when it touches
Okay, I got your point.
the ruler, yeah, will the ruler be pulled out a little bit? That changes the length you inserted.
Yes. However,
Yeah. Do you think this? Let's imagine this scenario. Do you think it will happen if there is angular momentum? Not talking about your experience.
okay, just if I think it was be also a good point to discuss, but in my experiment setup, I also control the position in the ball. So I think
if there is, imagination,
Okay.
there will be effect, right? And how do you think it will affect the possible results
I think
when the rotation is rotated by this point? The ruler's length is decreased, then what will happen in your own thoughts?
I think just this might be if the friction is too small, it might pull the ruler a little bit. But yes, I think we should focus on the search in my report.
Okay, so in this part, the opponents agree with the reporter that there will be deviation, and okay, let's imagine another part where this time the ball is pushed upward against the ruler. Is that possible? That there will be another phenomenon to be observed that the paper is and it strikes from the under. So.
I think this phenomenon will happen, but I think this is out of the conversation. So I think we can focus more on the result I have done in my report.
Okay, so then will the air final part that will the air drag force on the paper be a important factor that you should investigate? The air drag force. When the ball is pulled down and there is velocity of the ruler and this causes the air drag force, and is that an important factor in opponent's
Air drag force, you mean the downward force caused by the pressure difference?
No, the air's drag resistance.
You mean the air resistance?
Yeah.
So
In opponent's point.
I think the air resistance.
Sorry, we are out of time, so
Okay,
let's
thank you.
move on. So, opponent, please summarize the discussion for 1 minute.
Okay, so in the discussion part, we have discussed various conditions such as what factors can be added, like the reporter used the elastic ruler, and that in opponent's point of view, that is an important factor that need to be discussed, and also the ruler's oscillation, and also the tilting angle of the boundary condition is also discussed. And we also discussed some interesting facts that we can investigate more, like the part of rotation of the ball, and also we have discussed about the drag force, where the opponent offers the opinion about the drag force will be relative to the velocity that the ruler bounced out. So there will be a important factor that is able to for the reporter to investigate in the future. And that's all of my concluding. Thank you.
Okay. Now let's have the reviewer to ask questions.
So can I have the first one with you? So can we go back to the graphic Joe at the very beginning about the phase of the ruler flipping up, like just go to the very beginning of it.
Actors here.
It's got a motion of the ruler.
Oh, you mean the
Oh,
animation?
yeah, this one. So
okay.
so from your graphic, so are you saying that the air pressure is always up? The reason that air pressure applies on is for all
Yes, I
this.
think the air pressure just apply on the paper, but I think the real effect will be on like this area. That's the paper comes up. Because I think in those area, there's no pressure difference under the paper or above the paper. So I think this area will really affect this phenomenon.
And another is about you disagree with the opponent that the bullet is realistic. So which appears the bullet will bend, right? So as a proposed as the collision phase, the bullet might bend like this. And do you put so I think there will be other forces created, and would you put that in consideration?
So yeah, I have mentioned this before. I think there is some potential complexity. So we use the support coefficients to calculate the alpha, and I think this will consider about the bending of the ruler.
Okay, so I got one for you. So you were like talking about the air resistant force, and so what kind of like what do you think, how would it affect the force of the ruler?
So if we change the drop height of the ball, then the velocity of the ruler will change. So that the paper will experience different velocities that is lifted up. Then the velocity is relative to the air drag force, which the opponent thinks that will be a important factor.
Okay, so in your opinion, so you think the force caused by the pressure difference will be smaller as the velocity of the ball and leads to the ruler of the velocity increases. So the total force comes down from.
Yeah, so
that way it will decrease.
there will be another factor, yeah, just as you said.
Okay. Okay, so this is fine.
Okay, so prepare for the report. We have 2 minutes.
So, honorable judges and distinguished contestants, this is YC from the first team. So, I'll be reviewing problem 14 ruler trick. So, let's start with the problem statement. So, their main focus is on why exactly the ruler wouldn't fold and how much the fold. Just they talk about the critical force, right? And let's go on for the reporter part. So I think their advantages about they have the elaboration about the theory and their core experience setup, like they use multiple approach to calculate the forces that they want. And our suggestions about like I think there should be more variable big concept, like just like the opponent mentioned, maybe the inserted length of the ruler, or there's a lot of variable about the ruler and didn't take into consideration. And so about the opponents, I think they go into deep to the questions, like they navigate many things out of the reporter didn't consider. And I think it's great for like raising up like different opinions, but I think they could go into like because in their discussion we didn't get a really complete response or a conclusion. So I think that could be a further improvement. And so for the discussion, the opponents ask about the inserted length of the ruler and would that be a fraction. And so for the reporter, and they just in order to simplify the questions, they did not put that into consideration. But our opinions is that we do think that the factor of the inserted length would affect the whole force on like the creating force, like the value of the force. We all think that will change it, so I think they should take it into further consideration. And for the other, so the opponents raised that there will be, because they first asked if the ruler is elastic, so the reporter answered yes. So if there's they will create a deformation of the ruler. And so which leads to there will be like damping of the ruler created, and which reduce the force caused by the collision of the ball. So the reporter didn't take that didn't take that much into consideration. So in our opinion, we do think like because the ruler is elastic, so the ball might remain on the ruler, and there might be like forces damping, like direct force or causing, but they did not take into consideration. So I think that could be a further improvement. So this is my reviewing. Thanks.
Now finally, we will have concluding remarks from the reporter.
Okay, here's a concluding remark from the reporter. Okay, so in our discussion we use the low pressure bucket to analysis and the equation of critical force and other simulation to discuss about the phenomenon. And we also use the various parameters over here to discuss the phenomenon. And then here's my conclusion: the structure model will be closer to a theory, and then when the length increases, the critical force will increase. The ratio closer to 1, the critical force will increase. So and the math also will affect this phenomenon. And here I want to discuss about critical point that's the opponent keep asking me about the depth of the ruler. So I want to demonstrate it. Okay, so right over here, actually, we have discussed about I think that this distance will affect this phenomenon more, because in our simulation you can see that these two will flip and these two won't flip, but they are all same area. So I think the main points that affect this phenomenon will be this distance. If the distance is too big or too long, that the ruler will be not easy to flip. And also, I have discussed about the other variables in our experiment, but because of the time, I have not time to explore or present more about. So, okay. So here's my concluding remarks. Thanks.
Now let's take a question from the jury member. Yes.
I want to speak. It's about you. Have you ever done an experiment? Just put your ruler and just don't drop the ball. Just put the ball here.
Oh, yes.
Yeah, and what will happen?
I think-
Just measure the force and when you will flip.
Yeah, I
What's
have.
the difference?
Just if we directly place a ball on this, the ruler will directly fall. And I think this is because of the contact time. So if the contact time is too big, that we can simply just analyze it like a torque balance. Just if we directly place a ball on the ruler, it's just like a question about torque balance. So if the ball, yes, like a seesaw. So if the ball is heavier than the paper, that the ruler will.
For the opponent, we agree with the reporter where there will be surely a seesaw model that can explain the folding of the ruler.
I agree with both of them. So basically, there will be a total balance there. So like I think I don't know so much, so because our opinion is just a part of the sentence.
Okay. Any other question?
According to the statement, if I get it correctly, so you mentioned the deformation of the ruler doesn't matter. How is that correct? Deformation of the ruler.
Oh, I think that would affect just but we consider the bending of the ruler just adding the support coefficients. So I think that our experiment data still have a certain amount of accuracy. So but I think yes, it will affect. Yeah, it also.
I need to change the type of the ruler to check the function.
You mean tracker?
Different type of ruler.
Oh, different type of
Different type.
different type of ruler. Oh, I didn't do the different type of ruler, but I do the different type of. Yeah, I didn't do different type of ruler.
Yes. For opponent view, we think that if the deformation is bigger, then the oscillation is bigger, then which the oscillation will cause the energy loss of the whole system. And the energy loss will determine the final bounce of the ball and the phenomenon, which is important.
Yeah, so for that one, so that's just the reason why I said about why they did not do like the same experiment under a different material of the ruler. So it might bend differently, so the force will cause differently. So I agree with the opponent.
That's a more technical question for the reporter. So in page 20, so you define you use the whether if the paper comes out of the table to connect. What's the concept definition?
So in this definition, I want to define what is a flip because in our report, our goal is to analyze how many forces is needed to make the ruler flip. So I have to define what is flip because sometimes that the ruler will fall off the table. However, the paper still remain on the table. So I don't think in this condition the torque from the ruler has fully overcome the torque from the air pressure. So I think I think if in this situation, that means the torque from the ruler just overcome the torque from the other branches. So I will define this as a flip.
I'm a bit confused because the main object is the ruler, but we kind of use the paper to define this.
I think I define the movement of the system because also there's another and there's another condition that is a table and there's a ruler and here's the paper. So there's a condition when here will be friction force right here. So if like the ruler deflection like this, and if the friction at this point is too small, then the mass of the ruler will make it just sliding down of the ruler. But in this condition, the torque from here didn't overcome the torque from here didn't overcome the torque from the air pressure and the mass. So I didn't. So I defined this not the.
Okay, thank you. Our time is up, so let's move on to the second part. Everyone ready? Okay, so let's show the grade. For the reporter, yeah, first. Alright, so begin with me. 6, 9, 7, 9, and 7. Now for the opponent. I think it's 7, right? 6, 7, 7, 8, and 7. And finally, for the reliever, 5, 7, 8, 6, 7.